Are you ready?
Yes, yes, I am.
Very good. Okay, introduce yourself. Um, I was too rude to give a little bit of background to professional background to the folks who have presented so far, but save a few seconds about that. And of course, your title of your talk, and your time is beginning now.
Yes. Hi, so my name is Zoe de Beurs, and I'm a senior at the University of Texas at Austin. And today I'll be talking about my research in removing stellar activity signals using neural networks and other machine learning techniques, where our big picture goal is to increase our sensitivity to smaller and smaller, potentially habitable Earth-sized exoplanets. So as a reminder, in the radial velocity method, planets introduce translational shifts to the average line spectrum as the star is moving towards us or away from us due to the gravitational pull of the planet. And we measure this average line spectrum by calculating a cross-correlation function, or what I will refer to as a CCF, between that spectrum and a template of delta functions. And we can measure these translational shifts using precise spectrographs to infer details of a planet's mass or orbit. However, planets are not the only thing that can result in changes of the CCF. Stellar activity, such as sunspots, which are these dark regions on the surface of a star, can change the line shape of the CCF, as you can see in this animation on the right. And when this line shape is changed in this way, these stellar activity signals can mimic or hide translational shifts. And it's important to note that these stellar activity signals can be several orders of magnitude larger than the signals of Earth mass exoplanets. And so it's crucial that we characterize and effectively remove this stellar activity so that we can actually become sensitive to these smaller planets. So our solution to this problem of stellar activity, oh, one moment. So our solution to this problem of stellar activity is to train a neural network to recognize these subtle shape changes caused by stellar activity. So neural networks are a class of artificial intelligence algorithms that are considered state of the art for shape recognition. And neural networks take a specific input, and then the activated neurons will learn to extract specific patterns in those observations and finally predict a stellar activity signal or a specific output. So what information do we give our neural network to predict the stellar activity signal? So we are using, um, sorry, I think my slides are getting stuck for a second. We are feeding our neural network the CCF that I discussed earlier. So on the image on the left here, we have a cross-correlation function that corresponds to this SDO image of the sun that has a specific spot. But as you can see, it's difficult to tell this image apart from a quiet observation where there are no spots on the surface. And so what we do is we subtract this quiet reference from the observation of interest to get a residual CCF. And then we normalize this and feed that into our neural network. So this is just one example, but neural networks require a training set. So we are using a training set of about 600 daily observations of the sun from the HARPS-N Solar Telescope. And then for hundreds of these observations over here, I'm plotting them, and they are color coded based on how red-shifted or blue-shifted the signals are due to stellar activity. And you can see a pattern emerge where certain shapes correspond to the activity signal. So we are training our neural network to systematically predict and remove stellar activity signals from the sun with the hope that it will teach us how to do this for other stars. So you may wonder, how well can you do this for the sun? So we found that for solar observations, we were able to reduce the RV jitter by a factor of 2 using 3 different machine learning methods, where we found that the most complex model, the convolutional neural network, performs best, reducing the scatter to 0.78 meters per second. When we look at these results in Fourier space, we have these nice periodograms which will show us strong signals. So for example, on this top panel, we have the uncorrected radial velocities, and we have a strong signal at the star's rotation period, at half the rotation period, a long-term magnetic signal, and some activity aliases. And all of these signals disappear in the corrected RVs, indicating that the reduction in RV scatter is because we are systematically predicting and removing stellar activity signals. However, the big question is, can we learn from the sun and adapt this method for nighttime observations? So we had a specific test case of a bright star with a validated planet, which was observed with
Zoe,
K2.
1 minute, Zoe.
Thank you. So we had a specific test case of a bright star with a validated planet, which is observed with K2 and TESS, as well as HARPS North. And although this planet has been validated with the transit method, the RV measurements were relatively noisy, and we haven't been able to confirm a mass in the past few years. So we wanted to see if our method could help. And from a very preliminary result, we do see an improvement where before our activity correction, we got about a 2.3 sigma detection, and afterwards about a 4 sigma detection. And I'd be happy to talk more about what methods we were exactly using for this specific star, but for the sake of time, I'll move on to my conclusions. But again, I'd be happy to take questions about this. So in conclusion, we found that machine learning methods can remove stellar activity signals and reduce RV jitter by a factor of about 2 for our sun, paving the way towards higher precision RVs. And in the future, we want to continue the synergy between solar observations and extrasolar observations to further the goal of mitigating these stellar activity noises, which will ultimately help pave the way towards detecting smaller and smaller planets around bright nearby stars. I'd like to thank my advisors and many of the research groups that I had the opportunity to be a part of. Thank you.
Great, very good. Nice list of acknowledgments there. So thank you. That's always very, very good. Compliments, not too surprisingly, compliments on Slack. We got a couple of minutes. So why don't you go ahead? You said that you wanted to say a little bit more about the technique and the process. So we've got time. So yeah, go ahead. Take a couple of minutes.
Yes, I would be happy to. Yeah, so I think one thing that's really important to note is when we're looking at, okay, can we do this for the sun and can we do this for a extrasolar star? We are dealing with very different numbers of observations. So for the sun, we have daily averages where the sun was observed almost the entire day, and we have roughly usually after we check for quality and check for which observations we want to include based on specific parameters, we usually have about 50 observations for a single day. And then for our training sets, we had like 600 days that we were doing this for. Whereas for an extrasolar star, you're not going to have such an abundant data set usually. So like for this bright star, for example, we had about 80 observations with about one per night. And this poses some challenges because you can't necessarily use your traditional neural network machine learning methods because you wouldn't necessarily have like a large enough training set to train on. So instead, what we're using is a linear regression approach where we are simultaneously fitting four specific parameters in this like cross correlation function. I actually have like an extra plot that explains it a little bit better. So over here, this is what the cross correlation function looks like for the extrasolar star that we're looking at. And then we're using specific locations in that CCF to simultaneously fit these proxies for stellar activity and Keplerians. So it's a little bit of a different approach. But yes, I don't know if there's more questions about that.
There are. There are a whole bunch of questions, compliments too. Let me ask one question, and then Zoe, when you leave, when you wrap up, go to Slack, and because you've got a bunch of questions, I'm going to ask one that begins with "Great work, Zoe. Can you remove flares also from the data with your work?"
That's a good question. We have not
A little
tried that
tougher, a little
specifically.
tougher. Go on.
Yeah, it might be a little bit more difficult. We haven't actually tried that, but I guess the question would partially be whether you can actually see those flares in shape changes of the CCF, because I would imagine that sometimes flares, depending on which side of the star they're coming off, they can either result in it being more blue shifted or red shifted. I'll have to think about that a little bit more, but
Okay.
I appreciate the question. Yes.
Yeah, good question. As I said, they're on Slack. Okay, so they're on Slack. They're Slack. So I think it's time to transition to the next speaker. Thank you so much.